Coagulation is quite a complex process. By adding some flocking agent to the water, dissolved material within the water is forced to build flakes, which will eventually sink to the ground in a sedimentation basin after the coagulation tank. We will not describe this process here in detail. If you are interested in learning more about this process, we can recommend lectures in water treatment. In a real water treatment plant, coagulation would take place in a cascade of basins. For this unit, we will limit ourselves to modeling the coagulation process according to some parameters that have been determined statistically. Also, we will limit ourselves to modeling the water parameters. In a real water treatment plant, of course, you also have to take care of the control of the process of mixing the flocking agent into the water and of mixing the water itself. Thus, our model will be a simplified one. The first process we have to consider is the adding of the flocking agent. Instead of modeling the whole dispensing system for the agent, we assume that always the correct amount of agent is added to the water. In a study conducted at the University of Dresden, it is described that the amount of flocking agent that has to be added to the water depends on the concentration of dissolved organic carbon, so that at the end of the process we get the desired concentration of the agent. This desired concentration has been determined empirically. Thus, we model. The concentration of the flocking agent in the water in milligrams per liter is given as shown on the slide. This amount of flocking agent also adds to the dry matter contained in the water. Be aware that the concentration of the dry matter is measured in grams per liter. Therefore, before adding the concentration of the flocking agent to the previous concentration of the dry matter in the water, we have to divide the computed concentration of the flocking agent by 1000. In our model, we assume that we use polyaluminium chloride as a flocking agent. Thus, the use of this agent has an effect on the concentration of both aluminium and chloride in the water. In its molecular structure, the flocking agent has got 12 aluminium atoms. The molar mass of this agent, polyaluminium chloride, is 1157.6 grams per mole. Considering the molar mass of aluminium, which is 26.98 grams per mole, the fraction of aluminium in the whole molecule is 28%. Thus, we compute the concentration of aluminium in the water depending on the added amount of flocking agent as follows. The concentration of aluminium in milligrams per liter is computed by multiplying the concentration of the flocking agent, also in milligrams per liter, by 0.28. By adding the flocking agent to the raw water the aluminium adds to the one that is already contained there. Therefore, the concentration of aluminium that has been computed as above adds to the concentration that is already contained in the raw water, and the result replaces the previous concentration of aluminium in the water. So the new concentration of aluminium in milligrams per liter is the old concentration in milligrams per liter plus the concentration of the flocking agent in milligrams per liter multiplied by 0.28. Like the aluminium, the molecule of the flocking agent also contains 12 chlorine atoms. However, the molar mass of chlorine amounts to 35.45 grams per mole. Therefore, the fraction of chlorine of the whole molecule is 36.8%. Thus, the concentration of chlorine in milligrams per liter is computed as the concentration of the flocking agent in milligrams per liter multiplied by 0.368. Again, this value represents the additional concentration of chlorine induced by the addition of the flocking agent. As with the aluminium, the computed value for the concentration of chlorine will be added to the initial concentration of chlorine in the raw water, and this initial concentration will be replaced by the newly computed sum. This means the new concentration of chlorine in milligrams per liter is the old concentration in milligrams per liter plus the concentration of the flocking agent in milligrams per liter multiplied by 0.368. The precipitation reaction caused by the coagulation also eliminates previously dissolved organic substances from the water. This leads to a decrease in the concentration of dissolved organic carbon, or abbreviated DOC. A logarithmic correlation between the concentration of the flocking agent in the water and the DOC reduction has been found out empirically. The formula shown on this slide approximates this result. Again, all concentrations are given in milligrams per liter. By the use of the flocking agent, the suspended particles that were initially dispersed in the raw water are clogged to larger units. Therefore, the dispersed particles that cause the turbidity of the water disappear. In a work of Gao and others from 2005, this correlation was examined empirically. The approximating formula that describes the turbidity of the water when it leaves the coagulation basin, and that is shown on this slide, is based on the results of this work. In the sedimentation process that takes place in the sedimentation basin where the water flows when it leaves the coagulation basin, the size of the sludge flakes that were formed in the coagulation basin is an important parameter. Therefore, we want to compute the size of these flakes here approximately. In the coagulation basin, the flocking agent at first causes the formation of microflakes. While the water traverses the coagulation basin, microflakes adsorb to other ones, thus forming larger flakes. By this mechanism, the flakes grow over time until they reach a critical size that cannot be exceeded. This means that the size of the generated flakes significantly depends on the detention period of the water in the coagulation basin. In experiments, Zhang and others identified this correlation. It is approximated by the equation shown on this slide. Please note that the diameter of the emerging flakes is computed in micrometers. Build a subsystem in Simulink that represents the coagulation basin. This basin consists of several other subsystems. One that computes the amount of added flocking agent, one that computes the amount of dry matter added to the water, one that computes the turbidity of the water when it leaves the basin, one that computes the reduction in DOC, one that computes the flake size, and one that computes the concentration of aluminium and chloride in the water, respectively. In your model, you need at least the subsystem that computes the amount of flocking agent added to the water, the subsystem that computes the additional amount of dry matter, the one that computes the reduction in DOC, and the one that computes the flake size. The other subsystems are optional. Integrate your subsystem into your complete system of the plant, which has already been implemented, and instrument the simulation model at will.